Welcome back to Bite-Sized Breakthroughs, everyone. Today we're diving into a fascinating paper that tackles a critical challenge in the world of deep learning: how to efficiently train these massive networks, especially as they grow increasingly complex. That's right, Alex. Our guest today is Dr. Paige Turner, a leading researcher in the field of deep learning parallelization. Paige, thanks for joining us.
It's a pleasure to be here, Alex. I'm excited to discuss this research, which explores ways to go beyond traditional parallelization methods and achieve significant speedups in deep neural network training.
Let's set the stage, Paige. Can you provide some historical context for this research? Why is efficient training of deep neural networks such a crucial problem?
Sure, Alex. Deep neural networks have become the driving force behind remarkable advancements in fields like image classification, speech recognition, machine translation, and even game playing. But these sophisticated models, along with the ever growing size of training datasets, demand immense computational resources. Training these networks can take days, weeks, or even months on traditional hardware.
So, the need for parallelization becomes apparent. And we've seen common approaches like data parallelism and model parallelism emerge. What are the limitations of these traditional methods?
You're right, Alex. Data parallelism, which replicates the entire network on each device and processes subsets of data, works well for compute-intensive operations with few parameters, but struggles with operations involving many parameters. Model parallelism, on the other hand, assigns subsets of the network to different devices, reducing parameter synchronization, but limiting parallelism within an operation.
It sounds like a classic trade-off. This is where the paper's key contribution comes in. Paige, can you tell us about the SOAP search space and how it addresses these limitations?
Absolutely, Alex. This paper introduces a more comprehensive search space for parallelization strategies, which we call SOAP, standing for Sample Operation Attribute Parameter. It goes beyond data and model parallelism by considering parallelization across all four dimensions.
Can you elaborate on each of these dimensions, Paige?
Sure. The sample dimension refers to how training samples are partitioned across devices. This is what data parallelism primarily focuses on. The operation dimension describes how different operations within a neural network are parallelized, which is where model parallelism comes in. The attribute dimension deals with how different attributes within a sample, like pixels in an image or words in a sentence, are distributed. The parameter dimension focuses on how model parameters are split across devices.
That's a lot to unpack. So instead of just replicating the entire network or splitting it into disjoint parts, SOAP allows for more flexible combinations of parallelization across all these dimensions. This seems like a significant step forward.
It is, Alex. Imagine you have an operation with many parameters, like a matrix multiplication. SOAP lets you explore strategies that parallelize it across the sample, attribute, and parameter dimensions, offering much greater flexibility than simply replicating the operation on every device.
That's a great example, Paige. But searching this vast space of strategies can be computationally expensive. How does FlexFlow, the framework presented in this paper, address this challenge?
FlexFlow is designed to efficiently search for the best parallelization strategy within the SOAP space. It uses a guided randomized search algorithm, specifically a Markov chain Monte Carlo (MCMC) algorithm. To accelerate this search, FlexFlow introduces a novel execution simulator.
Let's unpack the simulator, Paige. Why is simulation so important in this context?
Think about it, Alex. To evaluate a parallelization strategy, you usually need to execute it on the actual hardware, which can take significant time, especially for complex models and large-scale distributed systems. The simulator acts as a proxy, accurately predicting the performance of a strategy without the need for real executions. This makes the search process orders of magnitude faster.
That's incredibly helpful. How does the simulator work? What are the key assumptions it makes?
The simulator relies on several key assumptions, Alex. Firstly, it assumes that the execution time of each task is predictable and largely independent of the content of the input data. This is a reasonable assumption for many DNN operations based on dense matrix operations, but it might not hold for all DNNs. Secondly, the simulator assumes that the communication bandwidth can be fully utilized during data transfers between devices.
So the simulator essentially estimates the execution time of different DNN operations based on their type and size, and it uses this information to predict the performance of different parallelization strategies across a range of devices.
Exactly, Alex. And it uses a clever technique called delta simulation, where it incrementally updates a previous simulation based on changes made to the strategy. This significantly speeds up the simulation process, especially for large-scale executions.
This all sounds very promising, Paige, but it's essential to have a real-world validation of these claims. Can you tell us about the experiments performed in the paper and the results they yielded?
Of course, Alex. The paper evaluates FlexFlow on 6 real-world DNN benchmarks, including CNNs like AlexNet, Inception v3, and ResNet 101, and RNNs like RNNTC, RNNLM, and NMT. These benchmarks cover diverse tasks like image classification, text classification, language modeling, and machine translation. The experiments are conducted on 2 GPU clusters with different configurations, each with varying numbers of nodes and communication bandwidths.
So, what were the key findings? How did FlexFlow perform compared to other approaches?
The results are compelling, Alex. FlexFlow consistently outperforms both traditional data and model parallelism and expert design strategies, achieving up to 3.8 times faster training throughput. This speedup is achieved by effectively reducing overall communication costs and optimizing task computation time. The paper also compares FlexFlow against 2 other automated parallelization frameworks, Reinforce and OptCNN. FlexFlow outperforms both frameworks, demonstrating its ability to find more efficient strategies within a broader search space. In addition, FlexFlow's simulator significantly reduces search time compared to Reinforce, which relies on real executions and takes hours to find an efficient placement.
Wow, that's impressive. It seems FlexFlow strikes a good balance between achieving significant speedups and maintaining high accuracy. Professor Spectrum, as a field expert in distributed computing, what are your thoughts on this research? How does it fit into the larger context of deep learning parallelization?
This research is a welcome addition to the field, Alex. It tackles the critical challenge of efficiently scaling deep learning training to utilize the power of modern distributed computing resources. The SOAP search space offers a more comprehensive view of parallelization possibilities, and FlexFlow's efficient simulator and search algorithm are crucial tools for exploring this vast space. The performance improvements achieved by FlexFlow demonstrate the potential to significantly accelerate DNN training, opening up new opportunities for research and applications.
Professor, do you see any limitations in this approach? Are there any scenarios where FlexFlow might not be as effective?
That's a great question, Alex. As with any approach, there are limitations. The simulator relies on several assumptions, such as the predictability of task execution time and the independence of input data. While these assumptions hold for many DNN operations, they might not be valid for all types of networks or scenarios. The search algorithm is also a heuristic approach, so while it finds efficient strategies, it might not always discover the globally optimal solution, especially in very large search spaces.
It seems there's always room for improvement. Paige, what are the potential directions for future research based on this work?
Excellent point, Alex. There are several exciting avenues for future research. We could explore more sophisticated search algorithms beyond MCMC to further optimize the search process and find even better strategies. We could also investigate ways to relax the assumptions of the execution simulator to broaden its applicability to a wider range of DNNs. Finally, we could develop a more comprehensive evaluation framework that considers factors like memory usage and communication overhead, in addition to execution time, to provide a more holistic assessment of parallelization strategies.
Professor Spectrum, before we wrap up, can you highlight the broader impact and potential applications of this research?
This work has the potential to significantly impact the field of deep learning, Alex. It can accelerate DNN training across a wide range of domains, leading to faster model development and deployment. Furthermore, it can facilitate the development of larger and more complex DNN models, pushing the boundaries of deep learning capabilities. The automated parallelization optimization provided by FlexFlow can also streamline the process of DNN training, freeing researchers and developers to focus on model design and performance analysis.
That's a great summary, Professor. Paige, any final thoughts on this groundbreaking research?
I believe this research represents a significant step forward in our ability to efficiently train deep neural networks, Alex. The SOAP search space offers a comprehensive view of parallelization possibilities, and FlexFlow's simulator and search algorithm provide powerful tools for exploring this vast space. This work has the potential to revolutionize DNN training, enabling faster model development, deployment, and the exploration of even more complex models. I'm excited to see how this research continues to shape the future of deep learning.
Thanks so much to Dr. Paige Turner and Professor Wid Spectrum for joining us on Bite-Sized Breakthroughs today. This has been an incredibly enlightening discussion, and I'm sure our listeners will be eager to delve deeper into this important research. Remember, you can find more information on this paper and other deep learning advancements on our website. Until next time, stay curious.